We're now going to consider a general solution for a uniform electron gas without electron-electron interactions, but in a non-uniform field. And we're going to write as before, the non-uniform field, or potential in this case, is V of R. And we're seeking to know what spatial distribution of density that gives. The general solution requires a total energy, which is written as the kinetic energy plus the potential energy. Now the potential energy is relatively simple. We just use a simple straightforward electrostatics to say that EV is the integral dr of V of R, rho of R. And what do we do about the kinetic energy? Well, we start by remembering or recalling that the kinetic energy of a uniform electron gas, which is non-interacting, is given by epsilon Ke is 3/10 h bar squared over 2m into 3 pi squared rho to the 2/3, which we can write as alpha h bar squared over m rho to the 2/3, where alpha is given by 3/10 into 3 pi squared to the 2/3. That is the kinetic energy per electron for the uniform electron gas. So the kinetic energy density, the spatial density, is going to be given by that multiplied by rho, because if you do the maths, you'll see that the per electron multiplied by electrons per cubic volume, per electrons per volume, gives you density, energy per volume, is epsilon Ke multiplied by rho, which is of course just alpha h bar squared over m rho to the 5/3. Now the key approximation for Thomas Fermi theory is to assume that we can do something very similar to the potential energy, and we can write the kinetic energy Eke as the integral over the system of the kinetic energy density of epsilon Ke rho of R, which of course is just the integral dr alpha h bar squared over m rho of R to the 5/3. So this is a very interesting approximation. It allows us to calculate various properties of the system, and it's a local approximation, so it's assuming that the energy at each point is determined by the density at that point. This is something that we will come to see again when we get to density functional theory. So if we combine those two, we can write the total energy, E tot, as given by alpha h bar squared over m integral dr of rho of R to the 5/3 plus the integral dr V of R rho of R. Now in the usual way, we're going to find the ground state by minimizing the total energy. And in this case, what we're going to do is we're going to do that with respect to, WRT means with respect to, the density, the spatial distribution of the density. We have to impose a constraint at this point. We have to constrain the electron number, n, to be the integral of the density, or if you prefer, we have to constrain the density so that it gives us the correct number of electrons. Now, the way that we're going to do this requires you to understand two slightly more formal pieces of maths, the theory of Lagrange multipliers and also functionals. These are given in brief form, but with enough that you can understand what's going on in the notes in the appendices, and I would urge you to read through those and make sure you understand them. So what we're going to do now is we're going to consider the variation of the energy, and we're going to assume that at the ground state we can consider terms only linear in the variations of the charge density. So we're only going to consider linear terms in delta rho. And so when we've done that, using the theory of functionals, we can write the following. Delta E total is equal to alpha h bar squared over m 5/3 of the integral of rho to the 2/3 delta rho dr, and you should notice that both of these functions are functions of r. Plus the integral v of r delta rho of r dr. So that's the variation in the total energy. Now, if we had no constraint, we would set that equal to 0, but we do have a constraint, and so with a constraint, we require delta E total minus mu, which is a chemical potential, it's the Lagrange undetermined multiplier, delta N must equal 0. So that's the condition for finding the ground state energy, the minimum of the energy. And we write delta N is equal to the integral delta rho of R dr. So if we now combine that into an overall statement, what we say is the following. So 5/3 alpha h bar squared over m integral rho of r to the 2/3 delta rho of r dr plus the integral of v of r minus mu, those are both multiplied by delta rho of r dr, must equal 0. That's the condition to find the ground state of this system. Now, if we consider all possible variations, delta rho of r, the only way that that condition can be true for all possible variations is with the following. So we can say it's only true if 5/3 alpha h bar squared over m rho of r to the 2/3 plus v of r is equal to mu. We've done that simply by factoring out the terms that multiply delta rho and then rearranging. Now, if we substitute in for alpha, and simplify, we find the following. We find that we can write h bar squared over 2m into 3 pi squared rho of r to the 2/3 plus v of r is equal to mu, which is exactly the same formula as we determined when considering the simple example in the previous video where we had just divided the system into two halves with different potentials. So we now have a condition that allows us to find the charge density for the system, for this uniform electron gas. What we'll do in the next lecture is to consider what happens when we introduce electron-electron interactions, and we will again go back to the Hartree-Fock approximation. And having done that, we will have enough confidence in the general approach to then go on to density functional theory, which is a much more accurate approach than Hartree-Fock theory, and which will allow us to develop the theory of DFT.